Good afternoon, everyone. I'm sorry that I can't be with you today. I have an appointment that I cannot get out of, and I would much rather be working with you in school than taking care of this other bit of business, but that's the way it goes. So we're going to get started with Unit 6, and on Monday when I come in, I'll maybe give you a more detailed description of what the entire unit is about, but I would like to dive right in to the first lesson today. So hopefully you have your unit handout that's just been given to you. I don't mean to shout when I put the word factor up there like that. But factoring is what you need to always be focused on in this unit. If you are simplifying a rational expression, or you are multiplying two rational expressions, or if you're dividing rational expressions, or if you're adding rational expressions or subtracting rational expressions, or maybe you're solving an equation that has rational expressions in it. You need to factor everything first. If you do not factor everything to begin with, then you're going to be walking down the wrong road. And that road will not lead to success. So this is section 6.1, where essentially what we're going to do is learn what a rational expression is, write what we call equivalent forms of rational expressions, and then focus on simplifying them and stating what we call non-permissible values. Well, what a rational expression is an algebraic fraction where the numerator and denominator are both polynomials. Since a rational expression is a fraction, we need to be aware of the fact that the denominator is never allowed to be zero. You cannot divide by zero. And when you have zero in a denominator, that's exactly what you're doing. You're trying to divide by zero. Here are some examples of rational expressions. 3 over x is a very basic rational expression. P minus 2 over p squared minus 4 is a slightly more complex rational expression. And then this beast is certainly more complicated even than p minus 2 over p squared minus 4. Whatever you have learned about adding fractions on paper, not in your calculator, whatever you have learned about adding fractions is the same set of rules and steps that you would follow when adding rational expressions. Whatever you do when you're dividing fractions, you do the same thing when you're dividing rational expressions. So all I'm saying here is any rules you learn about fractions and operating on them, you use those same rules when you operate on rational expressions. Once again, you cannot divide by zero. The denominator of a rational expression is never allowed to be zero. The values of x, usually x, it doesn't have to be x, but the values of the variable that are not allowed are values of the variable that make the denominator zero. And we call that value of the variable a non-permissible value. So in order to gain appreciation for this, let's take a look at example 1. For each of the following, what are the non-permissible values? Well, when we look at this in factored form, and it already is, but I'm going to, be a little over the top here, and I'm going to write it entirely in factored form. Factored form means everything is multiplied by everything else. When you have things multiplied together, if any one of those things is zero, the whole thing becomes zero. So imagine that you change this p to the number 0. It doesn't matter about anything else because that p is a factor. And if that factor is 0, by definition of a factor, it means you're going to multiply that factor by the rest of the denominator. So you're going to be multiplying by 0 in the denominator, giving you 0 in the denominator. Similarly, if this happens to be 0, then the whole denominator will be 0. And what that leads us to is that the non-permissible values are p is not allowed to be 0 and q is not allowed to be 0. Those are the non-permissible values of the variables. When we take a look at this, what we're worried about here is the denominator, and I want to highlight the denominator. we're worried about this not being equal to 0. But just forget about this rational expression bit of business for a minute. If I said to you, solve this equation, forget about what's above. I just say solve this equation. What you would do is you would say that x plus 2 equals 0 and 2x minus 5 equals 0. We learned about this in quadratic equations. The reason is that to make this whole thing 0, if either of these factors are 0, if this is 0, it doesn't matter what the other factor is because you're multiplying by 0. You'll get 0. If this is 0, it doesn't matter what the first factor is because you're multiplying by 0, which will give you 0. And solving each of these little equations is child's play. Add 5 to both sides, divide both sides by 2, and you get this. So if I asked you, everybody, to solve this equation, these would be your answers. But we're not solving that equation. What we want to do is find the values of x that are not allowed. So I can change that to x plus 2 times 2x minus 5 is not equal to 0, and that leads to x is not equal to negative 2, and x is not equal to 5 over 2. These are the non-permissible values of that rational expression. What about something like 6y over 2y squared minus 18? In order for you to see the non-permissible values, you need to factor. So I can factor out of 2y squared minus 18 a 2. I notice that now that y squared minus 9 is a difference of squares. I think most of us can look at that and see that y is not allowed to be negative 3 and y is not allowed to be positive 3. I don't think we need to write y plus 3 is not allowed to be 0 and y minus 3 is not allowed to be 0. Those are the non-permissible values for C. X plus 6 over 2x squared plus x minus 10. Well, the key to success is factoring. X plus 6 over, and we're going to factor 2x squared plus x minus 10. It's got to be 2x and x. The 10 has to factor, I'm assuming, into a 5 and a 2. It's probably not going to be 1 and 10. So if it's a 5 and a 2, I can't put the 2 with the other 2. So this is my best option. And now what I have to do is ask myself if by putting negatives and positives anywhere, I end up with a product that matches the bottom. And if I FOIL that out, I get positive 5x and negative 4x, which gives me the x. Bottom line, we're graduating away from just lessons on factoring. Factoring is the first step, and you need to be able to factor that. Looking at the denominator, 2x plus 5 is not allowed to be 0. X minus 2 is not allowed to be 0, which leads us to x not being allowed to be negative 5 over 2, and x not being allowed to be 2. Let's talk briefly here about equivalent rational expressions. When a fraction is multiplied by the number 1, the resulting fraction might look different, but it's still the same as the original fraction. For example, if we take a look at the fraction 3 over 4, if I multiply 3 over 4 by 5 over 5, and 5 over 5 is 1, if I do that, I end up with 15 over 20. 3 times 5 is 15. 4 times 5 is 20. And that means that 15 over 20 is the same as 3 over 4. These two things are what we call equivalent fractions. The same kind of idea can be applied to rational expressions. For this rational expression, 5g over g minus 3, where g can't be 3, what are two different equivalent rational expressions? Well, we can do pretty much anything we want here. Well, not anything, but I can take 5g over g minus 3, and I can multiply the top and the bottom by 2. And what I get is 10g over 2g minus 6. So this rational expression that I have here is equivalent to the original rational expression. What's another one? Well, I mean, I'm not sure why you would want to do this, but you could take 5g over g minus 3 and multiply the top and the bottom by g. And we would get 5g squared over g squared minus 3g. All I'm doing is I'm multiplying that g through. So that's a second equivalent rational expression. We have introduced another non-permissible value by multiplying the top and the bottom by g. I wouldn't lose too much sleep over this. It's never going to pop up. But since we did include a new factor of g in the denominator, we should probably write g is not allowed to be 0. We could also put for these g is not allowed to be 3, because that was a non-permissible value that we started off with. State the operation and quantity that must be applied to both the numerator and denominator of the first expression to get the second expression. Well, the key here is writing the second expression, everybody, in factored form. If you take a look at the first expression, on the top of the first expression there's only a 7, and in the second expression there's 7x. The bottom of the first expression has x plus 5. The bottom of the second expression has x times x plus 5. There's an additional factor of x in the numerator and denominator. So the answer to this question is you're multiplying the top and the bottom by x. B, once again, the key is looking at things in factored form. We're going from 9 over r plus 1. We're going to 9r times r minus 1 over r times r squared minus 1. What I have done here, everybody, is I've started to factor that second expression. In the numerator, I can factor out a 9r, leaving me with r minus 1. In the denominator, I can factor out an r, leaving me with r squared minus 1. And I can go even further, because r squared minus 1 is r plus 1 multiplied by r minus 1. So we have to ask ourselves, what is in that second rational expression that was not in the first? And the answer is those things are in the second rational expression. So the answer to this question is you are multiplying the numerator and the denominator by r and r plus 1. All right, simplifying rational expressions. I've got a little exercise for us here. We want to simplify this fraction 1500 over 270 without using any fraction key on our calculator. Now, what you're probably taught in earlier grades is you can divide the top and the bottom by something. So, for example, your teacher in grade 9 might have said, well, I'm going to, and please do not write this. Don't write this. Your teacher might have done this. They might have said, well, I can divide top and bottom by 10. And if I were there in front of you, I'd look you in the eye and I'd say, are you getting that? Is that familiar? And I think everybody would say, yeah, we remember our teachers doing that. We're not going to do that. What we're going to do is the following. We're going to recognize that why that works is 1,500 happens to be 150 times 10, and 270 happens to be 27 times 10. And then what we're going to do is cancel them. And the key idea here is you are canceling a common factor. 10 is a factor of the numerator and a factor of the denominator. If we continue, and I say, well, what is a factor that's common to 150 and 27? Well, 3 goes into 150 50 times. And 3 goes into 27 9 times. So we can cancel these 3's. And we're left with an answer of 50 over 9. You know, you can certainly confirm on your calculator that if you take 1,500 divided by 270 and convert that to a fraction, that you do get 50 over 9. So, how do you simplify a rational expression? You do the exact same thing. If you see a factor in the numerator and an identical factor in the denominator, you can cancel them. For example, if you look at x squared minus 5x plus 6 over x minus 3, you could never, ever cancel anything until it's factored completely. Don't look at this and say, well, there's a 6 and a 3. I think I'll do some canceling there. You cannot do that. What you need to do is factor everything completely first. For example, showing you this, the numerator of this rational expression in your notes factors into x minus 2, x minus 3, and the denominator is x minus 3. I've just rewritten it so that we have x minus 3 in brackets, so that I can then point out to you that you have an x minus 3 in brackets multiplied by something on the top, and you have an x minus 3 in brackets multiplied by something on the bottom. It's multiplied by 1 on the bottom. But that means they're both factors, so they cancel. So you're left with x minus 2. Make note that I still have to say x is not equal to 3 because x minus 3 was part of the original rational expression. So example 4, this is the heart of the lesson. For each of the following rational expressions, state the non-permissible values and simplify the expression. Well, because of this factor, p is not allowed to be negative 3. Because if p is negative 3, that factor in the denominator becomes 0, which means the denominator becomes 0, and that's not allowed. This factor tells us that p is not allowed to be positive 3, because if it is, then that blue factor is 0, and then the whole thing is 0 in the denominator. Now we cancel common factors. The answer to this question is negative 4 over p plus 3, and p is not allowed to be plus or minus 3. The non-permissible values have to be stated and rewritten based on the original expression. We take a look at B. Well, this is a weird question. You certainly don't have to factor it, but I'm going to. I can write this as 2 times 3 times p times p times q times q times q over 3 times 5 times p times p times p times q. This is the same kind of thing we struggled with when we were looking at radicals and finding out how many factors of an identical quantity appeared under a radical. I just want to double check. I've got p squared and q cubed. 15, I think that's all good. The bottom line here is I have a factor of p and a factor of p, a factor of p and a factor of p. I've got a q on a q. I've got a 3 on a 3, which leaves me with, in the numerator, 2. The p's are gone. I have q squared. In the denominator, I have 3. Pardon me. In the denominator, I have 5. And I'm just left with a p. But I think most people could probably go from here to here in one fell swoop. Incidentally, p and q are both not allowed to be 0 because they were both factors in the original denominator. I want to talk about something that appears in this one. We have 5 minus k over k minus 5. These are not conjugates, but they are related to each other. If I factor a negative 1 out of the top, that 5 which is positive becomes negative, and that k which is negative becomes positive. And on the bottom I have k minus 5. If you like, just take a minute in your head and multiply that negative 1 back in to convince yourself that this is in fact the same as that. What this means is this expression is 2 times negative 1 times k minus 5 times k plus 3 over 3 times k minus 5 times k plus 6. And by factoring that negative 1 out, that allows us to cancel those k minus 5s. So in the numerator, I have negative 2, k plus 3, over 3, k plus 6. K is not allowed to be 5 or negative 6 because of the original denominator. So this is our answer to C. D, well, you cannot cancel anything until it's factored. Once again, the only reason in C we could go ahead and cancel stuff is it was already factored. Same with B. Same with A. So now all of a sudden we get to D and it's not factored. We have to use our factoring skills. So I can factor a common factor of 4 out of the numerator. The denominator, I can factor a common factor of 3 out. You should recognize x squared minus 9 is a difference of squares. So this is 4, x minus 3 in the numerator, 3, x plus 3, x minus 3 in the denominator, which, by the way, tells us that x is not allowed to be plus or minus 3 because of these denominators. However, our final answer after the canceling is going to be whittled down to 4 over 3 times x plus 3 with the condition that x is not allowed to be plus or minus 3. When you're simplifying a rational expression, basically you factor and cancel. It's that simple. If I could, boil this lesson down to the most important point, you factor and cancel. So here we have two basic quadratic trinomials. I call them basic because the leading coefficient of the quadratic term is 1. So all we're looking for here in the numerator is two numbers that multiply to give negative 10 and add to give positive 3. If you FOIL that out, you're going to get 3x in the middle. In the bottom, we're looking for two numbers that multiply to give 15 and add to give 8. We can cancel the x plus 5s. Our solution, or our answer rather, is x minus 2 over x plus 3. And x is not allowed to be negative 5 or negative 3 because of the original denominator in factored form. F, well, there's just a little bit more thought here. Once again, I believe this is the final example, but the deal here today is factor and cancel. There's other things we have learned here about equivalent rational expressions and non-permissible values. But when you cut to the heart of it, that's what you're doing to simplify a rational expression. These two rational expressions, these two polynomials are a little more complicated because of the leading coefficient not being 1. We have to go back to trial and error. Well, factoring a quadratic that starts with 2x squared must mean one of the binomial factors contains 2x and the other x. I'm guessing that the two numbers will be 5 and 3, and it's a matter of playing around with them. I think if you put 5 here and 3 here, you see very quickly that our target of negative x is out of our range, because when you start foiling that out right away, you're going to have 10x somewhere. So it's probably the case that this might work. And when I look at my outer term there, my outer product, I get 6x. When I look at my inner product, I get 5x. We want negative 1x, which means this 6 has to be negative, which means this has to be x minus 3, and that has to be 2x plus 5. Now here's an interesting thing. You would normally try 2x and 2x here. But, and this, I wish I could, be there with you to see your reactions, to see if you're understanding, but I'm going to throw it out there anyway. If I give you this question and I say simplify it, the only way I would give this to you and ask you to simplify it is if this 2x on the bottom matched with a 5, and then you could do some canceling. But on the bottom, these two numbers have to multiply to give 3. That's a fact. If I go back to the beginning here, these two numbers have to be a 1 and a 3. Why on earth would I ask you to simplify a rational expression if nothing canceled? So I would suspect that this will also be an x minus 3 on the bottom, which would make this a 4x minus 1. Both of those numbers, the 1 and the 3, have to be negative because they're multiplying to give a positive, and your middle term is negative. And if you FOIL this out in the denominator, your outer is negative 12x, your inner is negative 1x, and that is what I call a jackpot. You add those together and get negative 13x. So we can cancel these and write our answer as 2x plus 5 over 4x minus 1, and x is not equal to 3. And I think, well, sometimes I'm wrong in what I think about how students perceive things, but I think that's obvious, that to go from x minus 3 on the bottom to x is not equal to 3 is an obvious thing for everybody. To go from 4x minus 1 to x is not allowed to be 1/4 is maybe less obvious. What I'm doing there is I'm simply saying 4x minus 1 is not allowed to be 0. I add 1 to both sides, and I divide both sides by 4, and I get x is not allowed to be 1/4. So that's the lesson. I know in your handout it says 15, 17, 19, and 22. Don't worry about those. Do questions 1 to 4, A, C, and E, and then questions 6, 8, 11, and 13 are the important problems to practice. Probably the most important set of questions are 6 and 8, and in that, the most important is 8. Number 6 is asking you to simplify rational expressions But in number 6, everything's factored already. So somebody's done the hard work for you. In number 8, you're asked to simplify rational expressions, but it is not factored, so you have that heavy lifting to do, all of that factoring to do. It's never ideal when I'm trying to teach a lesson to an empty room. It's very strange to be standing here and teaching because I don't get any feedback from students. So my hope is that it went well today. If you have any questions, certainly we will be going over them on Monday when I see you next. So in the meantime and in between time, good luck with your math and have a fantastic weekend, and we will see everybody Monday. Take care.